Today, we're going to look at a multi-particle system, and we're going to, by the end, assume rigidity. So a rigid body of particles, and that's a stepping stone to a continuous rigid body. So instead of having each of the particles sort of these compact points, we assume something continuous, then we integrate. So a couple preliminary things. Before that, we need to talk about the energy and angular momentum of a multi-particle system, but from a slightly different point of view from the last time. So this is a multi-particle system. We'll be decomposing the total angular momentum and the total kinetic energy into the motion of the center of mass plus motion relative to center of mass. And these will have easier interpretations once we get to imposing rigidity. Right now, we're just assuming that we've got center of mass for a system and particles sort of moving arbitrarily around that center of mass. Things could deform. There could be all kinds of stuff happening. So let's start with angular momentum, and then we'll do kinetic energy. So this angular momentum, we could either call it a decomposition or separation. What we mean is there's an inertial origin. So there's our inertial frame. We've got the center of mass of a system of particles. Let's write the location of the center of mass. It says capital R, C. And then the location of each particle with respect to the center of mass, we denote that as little r sub I. So for each mass, and they have mass mi. So the total angular momentum, if we were to write the total angular momentum vector, is h with respect to the point O. Remember, for angular momentum, there always has to be a reference point. So h, O, I'll just give you the punchline. It could be written as the angular momentum of the point C with respect to O plus the angular momentum of the system with respect to the point C. And I'll write what each of these are, but let's just sort of summarize here. So this is the total angular momentum of the system with respect to the point O. This is the angular momentum of the center of mass, C, with respect to the point O. And then this HC over here, this is the angular momentum of the system about its center of mass. Or I guess we should say with respect to WRT with respect to C. Okay, and we could write expressions for each of these. H, C slash O is the total mass. Remember, M is the total mass. Sum over all of these. So from 1 to capital N. Total mass times RC cross RC dot. And just to remind ourselves, what do we mean by this over dot? We mean derivative with respect to the inertial frame N. So that's the angular momentum of the center of mass with respect to this inertial origin O. And then the other part is the angular momentum of the relative motion of the particles with respect to the center of mass. So we write that as HC. And this is a sum over the particles, 1 to n, mi times little ri cross little ri dot. And again, little ri dot is the inertial derivative of the, what is Ri? Little ri is the location of particle I with respect to the center of mass. So there we go. And we'll revisit these later. This is general. This is true for any system of particles. We could do the same sort of decomposition of the total into something of the center of mass plus relative to the center of mass for the kinetic energy. So let's do that. That needs to be more of a dot up there. These are dots. Okay, so total kinetic energy decomposition. I'll just say kinetic decomposition. Same sort of picture as up above. An inertial frame with the origin O, the center of mass, and particles. How did I write it up there? Okay, green. Sure. So here's Ri, and this is moving. So it's got some derivative, Ri dot. We've got the center of mass location, Rc, capital Rc, and that's also moving. There's Rc dot. So the total kinetic energy, we've written it before. We said it's the sum of 1 to the number of particles, 1/2 the mass times the inertial velocity squared. So this would be Ri dot. Sorry, not that. Forget that. This would be writing, if we say what each particle is in terms of capital Ri. So this is capital Ri dot squared. That's one way to write it, but it's sometimes easier to, like above, decompose this into kinetic energy of the center of mass plus kinetic energy of the system with respect to the center of mass. And this is, we'll write it, if you want, we're writing this kinetic energy up here. This is kinetic energy with respect to that inertial point O. So we'll write kinetic energy of the center of mass with respect to O plus kinetic energy of the system with respect to the center of mass. So just like up above, I'll label these. So this is total kinetic energy of the system. This is the kinetic energy of the center of mass. And this Tc would be kinetic energy of the system relative to the center of mass. So once we, if you think of a bunch of particles moving out in space, this kinetic energy of the center of mass, we'll call it, this is translational. It's translational kinetic energy. Whereas the second one is the kinetic energy of relative motion. That means motion of not this sort of straight line. The center of mass is moving, right, in some direction. It's got some instantaneous kinetic energy, but then you've got kinetic energy of the particles moving around. It's going to be something else. And like up above, I can write formulas for each of these. So the kinetic energy of the center of mass with respect to the point O, this is 1/2 the total mass, and then the kinetic, the inertial velocity of the center of mass squared. So the magnitude of that vector squared. What about kinetic energy relative to the center of mass? Similar thing to up above. It's going to be a sum of each of the masses. But now we're writing 1/2 mi Ri dot squared. And one of the things that we've used up here is that if you write the location of each particle, it equals the location of the center of mass plus the location of the particle relative to the center of mass. That's what we get for the two formulas. All right. So with this in mind, and I guess if you want to know where this is, at least for the kinetic energy to follow along, this would be in 2.51. They don't write it, I think, as nicely as I do, though. So this will include things like when we showed that movie of the galaxies colliding, and you've got this stretching and particles going every which way. Well, now we're going to make a big assumption, which is that we don't care if n is, Avogadro's number, 10 to the 23rd or something. We're going to impose rigidity. And imposing rigidity leads to huge simplification. And fortunately, like when we deal with metals and objects, right, we can assume that they are rigidly attached to a good approximation. You might say, oh, what about flexibility? Yeah, there's flexibility, but as a first approximation, let's assume that things are rigid. So we're going to impose rigidity and see how that affects these formulas and affects the dynamics. We're considering a rigid body of particles. So we're taking our same multi-particle system, sort of the general multi-particle system, but imposing rigidity. So what the image to have in mind, I don't know if people use Tinker toys anymore, but back in my day, there were these wooden things where you had sort of large masses connected by sticks, right? So think of the large masses are the particles, and they're now rigidly attached. What does that mean in terms of our formulation here? It means that the location of any particle, so if here's my multi-particle system, let's call this particle I, and here's particle J. So here's the location of particle I with respect to J. It's a vector location. And I don't know, there's a bunch of these. So we're saying that the magnitude of that vector is constant for all I and J. So I and J label the particles. So this is true for any pair of particles. So you could basically just imagine there's this rigid attachment between any pair of particles. And so you get the same picture as we get from these toys. So a rigid body, and this is equivalent to saying that the time rate of change is equal to 0, right? If the magnitude of a vector is constant, then the time derivative of the magnitude of that vector equals 0. So by rigid body, we mean a collection of particles constrained to be motionless relative to one another. So for example, in a kilogram of steel, here's a picture of some steel. Inside of this are, I don't know, a lot of atoms. I'll say 10 to the 25, something ridiculous, right? We're not going to deal with 10 to the 25 particles. So the nice thing is that nature conspires through rigidity to simplify this for us. So instead of having to deal with 3 times 10 to the 25th, X, Y, and Z coordinates, we have much fewer. At some level, matter does look like Tinker toys. Here's a picture of a crystal type structure. I don't know what crystal is. This isn't necessarily steel. It's just giving you an idea, right? Atoms on the whole seem to be motionless relative to one another. And that's a good thing for us. It simplifies the dynamics. So we might just say, we don't often think about like, oh, rigid bodies are amazing. But they are. So nature conspires, it conspires through rigidity to simplify dynamics for us, at least for solid objects. So we've got now, instead of having to deal with each of these individual particles, all we have to track is the center of mass and then a frame that we attach to the center of mass, attached to the rigid body. So we only need to track a point on the rigid body, or the center of mass might be a convenient point, but maybe that's not the only one. And the orientation of the rigid body, or attitude. And the way that we do that is we attach a body fixed frame. Usually we call that B. And then we're dealing with the orientation of a frame. Let me get my arrows for the blue frame that I'm going to attach to a rigid body. All right, here's a rigid body. Attach a frame to it. Now, to describe the motion of the rigid body, I just have to describe the motion of a point on it, or the center of mass inside there, and the orientation of a frame attached to it compared to an inertial frame. So that's sort of the essence of rigid body kinematics. The dynamics has to do with the mass distribution and angular momentum and other things. But there we go. One thing at a time. So I'm going to start with having you think of a rigid body of particles before we go to the continuous limit. So think of particles are all frozen and we attach a frame to it, right? This is rigid body. It's a multi-particle collection that moves like a coherent body and moves rigidly, so we call it a rigid body. Let me give you a concrete example where I don't have 10 to the 23 particles, but maybe 4. 4-particle rigidly attached system. Here it is. So we've got 4 particles here, and 3 of them are mass m. One of them is mass 2m, and they're connected in such a way that they're at some of the corners of a parallelepiped, like shown here. So there's this point O, and then there's a mass there, right here. And then a distance a away is another mass. So think of there being this massless wire frame that's rigidly attaching these particles together. With respect to a point on the body, for example, that point that we've called O, the only possible motion is rotation. So with respect to this point O, let's say this other point over here, maybe I'll color it blue, that can only rotate with respect to the point O. If you want, it's as seen from an inertial frame. So yeah, this gets to the point that we need to define some frames. So we should probably attach a B frame, some frame attached to this parallelepiped thing. So I'll call that the B frame. So call that B1, and then this direction, we'll call that B2, and then the direction going up this way is B3. That's attached to the body. There's also an inertial frame, and I know people get bent out of shape thinking of them being at the same origin or not. Just think if there's some directions, reference directions that aren't moving, they're on the table. I have a table in front of me, and then we've got this frame that's attached to the body. The only possible relative motion is rotation. So we've got a body fixed frame. So B frame is attached to this rigid collection of particles. And the B frame can rotate if you want, we're just talking about the B directions with respect to the N frame, which, sure, let's give them some names. N1, N2, N3. I guess we could start naming these particles if we want to. So if I call this particle, this one there, we'll call that 1, call that 2, call this particle 3, and then up here, this is particle 4. We could write the location of each particle with respect to some reference point, the point O. And then the only possible motion of each point is going to be rotational motion. So if we, let me write a vector that says, write R2 with respect to O. So that's this thing, R2 to O. And I'll just write that as, it's just R2 to make life easier. Then the way this moves, or we call that R2 dot, with respect to the inertial frame, it has to be, the only possible motion is some, due to rotation. And the way that we've described rotation is we say that right up here, the B frame can rotate with respect to the N frame, and there's some instantaneous angular velocity of the two. So we'll call that omega. In the terminology that we've developed, we do these little subscripts. So this is omega. It's the angular velocity vector of the B frame with respect to the N frame, meaning the B unit vectors, which form a triad of unit vectors with respect to the N triad of unit vectors. So over here, what is this? This can only be omega cross R2. And if you're confused, you can go back to lecture 3, where we said that, if you've got a point fixed on in a rigid frame, or a frame that's rotating with respect to another frame, that's the only type of velocity you get. You could think of this as coming from the transport theorem, but you could also just go back to lecture 3. Now, why is this important? This is important because when we now, when we want to write the dynamics, we're eventually going to have to write it's going to be based on the angular momentum of the rigid body. And the angular momentum of the rigid body, we could write it in terms of, if you remember from up above, it's the mass times position vector cross the inertial velocity of that vector. But whereas before the inertial velocity was kind of arbitrary, now it's constrained to be an angular velocity vector times that position vector. So the relative motion of the system of particles, this rigid system of particles, will be rotational motion. Before we imposed rigidity, the particles could go any which way. So you could think of it as like a deformable body. But now, with rigid attachment, only rotational motion is allowed. And so that's going to have dynamics related to the angular momentum and how it changes. At this point, we've got this reference point O, so we'll say HO, and then the dynamics will be related to how that changes in time. Time rate of change of the angular momentum. So let's write what the angular momentum is for this system of particles. It's 4 particles, so this is going to be a sum. I goes from 1 to 4 of Ri cross, well, the way I wrote it up above is I put the mass in the front. Mi Ri cross Ri dot. But now we'll use the fact that because of rigidity, the angular, the inertial velocity of Ri is related to the angular velocity vector cross Ri. So do the sum from 1 to 4, mi Ri cross omega cross Ri. And so this is a product of cross products. We can rearrange things. So I'll just use the property of the cross product that if you reverse the order, you pick up a negative sign. So 1 through 4, mi negative Ri cross Ri cross omega. And why do I want to do that? Because now I'm going to use the way that we saw from lecture 4 to write the cross product as matrix multiplication, because that's going to simplify our lives a lot. So from lecture 4, we learned we can write the cross product in matrix form. So for example, in this case, if we've got Ri, and let's say we're going to write this in the B frame, the body fixed frame. So maybe we'll call this, xi, yi, zi. It's the x, y, and z components for particle I. Same thing for omega. We'll want to write omega in terms of the B frame components. So omega 1, omega 2, omega 3. In fact, this might be easier if instead of writing it as xi, probably should do something else though, like ri1, ri2, ri3, just to make it easier to remember. We defined this thing that we called it was like the tilde matrix. So ri, the tilde, has zeros along the diagonal. And we're just reminding ourselves with that subscript B that we're writing this in the B frame. And this will be negative Ri3, positive Ri2 up here, and then negative Ri1. This is a skew symmetric matrix, so on the other side of the diagonal, we flip the signs of things. Then that means, I'm going to move this up here and make it small because I can. Give myself more room. Ri cross omega can be written as Ri tilde times omega as a column vector. So this same matrix, negative Ri3, Ri2, negative Ri1, Ri1, negative Ri2, Ri3. And we're just reminding ourselves with the subscripts that this is all in B frame components. And you can write out what that is. It'll give you the cross product. The main thing we're going to focus on here is, okay, we can write this first piece in using this matrix multiplication way. We could also write the second piece that way, right? Because we've got a cross product of a cross product. So that means that Ri cross Ri cross omega becomes, I guess I didn't put a subscript B up there, Ri tilde times Ri tilde times omega as a vector. And I think we had a minus sign out in front, so we could put minus, minus, minus. So we're going to define, if you remember what this was up here, this was angular momentum with respect to point O for the system. We're going to define something we call the, it's a 3x3 matrix. I'll call it capital I, O. And I'll say that this is negative mi Ri tilde times Ri tilde This is a 3 by 3 matrix. And it gives us a way to write that the angular momentum, HO, equals, it's going to be a sum, I goes from 1 to 4, of this matrix times omega. And the book is sometimes not careful about how it's, what frame things are getting written in. But we're writing the angular momentum vector in terms of the B frame. Now, what's the advantage of this? We've got the angular momentum on one side here equals something times the angular velocity. And this something in the middle, it's a sum related to where the particles are, and you could calculate it. And interestingly, omega over here does not depend on I. So we could actually sum up these matrices separately. I called this I because it's related to what's called the moment of inertia. So we can sum these individual matrices to get a total moment of inertia matrix. And we'll call that moment of inertia matrix just capital I sub O without the subscript little I. And remind ourselves it's being written in the B frame. So I, moment of inertia with respect to the point O. In this case, it's the sum, 1 to 4, of these contributions due to each particle. And if you look over here, the way that we wrote it, it's kind of obscure. Like, what? Negative mass times these two bizarre matrices multiplied by each other. Well, when you work out what those two matrices multiplied by each other are, they work out to be pretty nice. So if I were to write out, this is moment of inertia due to particle I. This is negative mi r tilde I times itself r tilde I. Through some algebra, and this is what you'll get. You'll get overall the mass comes out in front, and then we've got the magnitude of that vector, the position vector squared, times the 3 by 3 identity matrix. So I'll write that as a capital 1, 3 by 3, minus Ri, and this is in the B frame, times Ri in the B frame transpose. So it's a matrix transpose. So if this is a column vector, this is going to be a row vector. So together their matrix multiplication is a 3 by 3 matrix. This is the 3 by 3 identity. So if you're not sure what that is, it just means it's a 3 by 3 matrix with a bunch of ones along the diagonal. Everything else is 0. Okay, so that's what each individual one is. And when you add it up for each of the 4 matrices, it ends up being, it's going to look like this as well. So we can then say, right, the moment of inertia, you add all of those up here, you get the moment of inertia for the system, the rigid system of particles. The angular momentum, being careful to remind ourselves, is written in the B frame, is equal to the moment of inertia matrix written in the B frame times the angular velocity written in the B frame. So instead of looking like that complicated thing from before where it was a sum of individual particles, because of rigidity, the inertial velocity of each particle is always related to the angular velocity. So this is the relationship between the angular momentum and the angular velocity for a rigid body. We've got this matrix in here, which it turns out the moment of inertia matrix is a symmetric matrix, but this is still just, this is a 3x3 matrix. And we'll talk about its properties more later. Maybe right now, it'd be good to just compare how this looks compared to the linear momentum and its relationship to the linear velocity. With the linear momentum, right, we would write P equals, it's just the mass. So let's talk about the center of mass, I guess, is the total mass times the inertial velocity. So we're comparing with the linear momentum relationship to, we haven't really called it the linear velocity, but in analogy with angular momentum and angular velocity, this is the relationship of linear momentum and linear velocity. And here we don't have a 3x3 matrix, we actually just have a scalar, not a 3x3 matrix. And in some sense, that's the heart of what makes rigid body dynamics harder than translational dynamics of particles, is you've got these matrices floating around that are complicated, but they take into account how the mass distribution of a rigid body affects how that rigid body rotates, even in the absence of moments. When you've got moments on it, then things become even less intuitive. If we were to actually start calculating what this was, like you might be interested, how would I do this for that system of particles? I'll just bring it up again, yeah, with the frame attached. So if we were to actually calculate that, calculate the moment of inertia matrix with respect to the point O for this system, written in these B-frame components where we've got B1, B2, and B3 as they're shown here. Well, we would start with writing the contribution due to each particle. So like we wrote up above, it's the contribution from 1 to 4 of each of the particles. I think we called this particle 2. That's a 2. This is a 1. This is 3. And up here is 4 of these individual contributions. Now let's try the contribution of particle 2. Moment of inertia, particle 2, about the point O. Well, we've got the formula for that. It would be the mass of particle 2, which is just m, and then the magnitude of the vector, r2, squared times the 3x3 identity minus ri, right, this is r2, r2 written as a column vector in the B frame times r2 transpose in the B frame. Okay, what is r2 in the B frame? It is, well, it's just a distance a, and then in the B1 direction, and then everything else is zeros. Okay, and what is r2 B transpose? I guess let's remind ourselves it's in the B frame. This is a row vector. Okay. If I write the magnitude of r2, well, that's a squared. So r2 magnitude squared times the 3x3 identity is going to be a squared, a squared, a squared. Just a squareds along the diagonal. What about r2 times r2 transpose? It's a column vector times a row vector. And it gives us, like, the only non-zero component is this one in the upper left, the 1, 1 entry. And then everything else is zeros. All right, so just subtract that from this, and there you go. So I keep trying to remind myself that this is written in with respect to the B frame. So this ends up being M0, a squared, and then everything else is zeros. So then do the same for the other 3 particles and add it up. And you get a moment of inertia. This is for thinking of this pretend situation where we've got particles and we're attaching them by sticks, like the Tinker Toy situation. Of course, when you deal with actual matter, it's easier to approximate it not as 10 to the 25 individual little particles, but as 10 to the 20, whatever it is. I don't know how many particles are in here, but you do a continuum, a continuous mass distribution. So instead of thinking of discrete masses, we go to a continuous limit, and instead of a discrete sum, we have an integral over mass elements or integral over volume elements. I guess it's worth looking at what you get there. Okay. When we want to look at continuous systems, and this is in section 2.5 of Schaub and Junkins. They treat it slightly differently. When we go from discrete masses, right, with some rigid body attached, rigid body frame, I mean, and we go to a continuous limit. So instead of lumps of particles, we have continuous limit. So this is a continuous mass distribution. Maybe we don't know initially where to start. We pick some origin. It might not be the center of mass, but you need to start calculations somewhere. Like if I hand you an object, you got to pick some kind of reference point on it to start calculating things. So with a reference point, like this point O, then you can define your body fixed frame. So it's a frame fixed in the body. And instead of individual masses, discrete masses like we had here on the left, now we've got tiny volume elements or mass elements. So you could call this dm. dm is an infinitesimal mass element. We might refer to this body by fancy script B, so that instead of over here, before we had to sum over discrete masses, a sum, right? When you go to a continuous limit, you're taking an integral. So you have an integral over the body B and infinitesimal mass elements of whatever it is. So here we would be summing over something. Here we'll be summing over something. Summing over some property at each of these mass points. Maybe it has something to do with the location of each mass point. Let's call that R for now. The book seems to deal with mass elements, but often when you're dealing with actual matter, you need to know the mass density. So an infinitesimal mass element is going to equal the density, and I'll write rho, it's a scalar rho, at that point, times a volume element. So this is the mass element. This is a volume element. And this is the mass density of the element. Right, so that gives mass per unit volume. And often, dV could be written in different ways depending on what your coordinates are. If we use the usual Cartesian coordinates, right, this would be written as dx, dy, dz. So instead of thinking this is a single integral over individual mass elements, it might be a triple integral over dx, dy, dz. And we're allowing for the possibility that the density could vary throughout a body in theory, but often to simplify things, we'll treat it as its constant mass density, but that's not always true for something. For many materials it is, but you might just be aware that mass density could depend on where it is in the body. Right, so once we have a continuous mass distribution, we can write the moment of inertia if we really wanted to. So the moment of inertia matrix becomes an integral. So if we were to write, say, the moment of inertia for some body about point O, in the body fixed frame, this would be, I'm going to write it as a triple integral because it's volume, so 3 dimensions of, and I'm using little r to write things with respect to O. Here's 3 by 3 identity minus r times r transpose, and then dx, dy, dz. And we'll get into what this is later, because we're first going to do rigid body kinematics, but I wanted to give you an idea of, you know, where we're heading. We could even talk about what does the moment mean, the moment of inertia about a particular axis. We could think of it as representing how difficult it is to rotate something about that axis. So this is you know, the interpretation of the moment of inertia matrix. In previous dynamics classes, you probably just did rotation. We call it 2D rigid body dynamics. So you had the moment of inertia is just a scalar. So if you were thinking of like a rigid rod about its end, you know that there's a certain moment of inertia related to that. If this had a mass m and it had a length L, the moment of inertia for a slender rigid rod about its end is, it's just a scalar, and it's like 1/3 ml squared. Just a scalar, and it represents how hard it is. So here's something like a rigid rod. How hard it is to rotate something, the amount of force needed. So it gives a measure of the difficulty, just like mass is a measure of how difficult it is to get something moving translationally. Moment of inertia is a measure of how difficult it is, the resistance to rotation. But now you need to think not in terms of just a scalar, but you've got a matrix, and maybe the way that you've learned to handle matrices is, you know, that there are certain eigenvectors, right? So if we're writing the moment, the angular momentum is some moment of inertia. I'm doing everything B frame just to be careful. Here's the issue. If you have some rigid body and you've got an angular velocity, if you multiply that angular velocity vector by this 3 by 3 matrix, you're typically not going to get an angular momentum that's in the same direction. It'll be in some other direction. There are some special directions, though, where if you have omega in that direction, then h will also be in that direction. And these special directions are directions about which you can have pure rotation of the rigid body. So if I have a rigid body, I can't just rotate it. Here, I've got this vector. I can't just have it purely rotate about some direction. There's only 3 directions, 3 special directions, because this is a 3 by 3 matrix. It's a 3 by 3 matrix. So it has 3 eigen directions, 3 eigenvectors. And those are the directions where you get pure rotation. So actually for a rectangular body like this, it's the obvious directions. It's the normal to each face. If this had a uniform mass distribution, which, you know, more or less it does. So this, if I could get it spinning on the space station about an axis perpendicular to this face, if this arrow would stay put, it'll rotate purely about that direction. Without, you might be thinking, what other kinds of things happen? You could have something that looks like tumbling. Eventually we'll give it names like precession, but there are special directions where if you get it rotating in that direction, it'll look like pure rotation, not a tumbling type of motion. So it's a 3 by 3 matrix. The eigenvectors give special directions. or axes about which pure rotation is possible. No tumbling, and I'm just using that as a, not as a technical term, no tumbling or precession. They're not all stable either, and that has very important implications for satellites. Right? You don't want something spinning about a direction that's unstable. That means that if it starts spinning about that direction, it'll actually move away, and that's not good. So if I have a given body, so if this is a rectangular body, like a rectangular prism, then the directions are just the normal to each of the faces. That makes sense. It's not obvious what it is for some kind of arbitrary body. Like think of an asteroid with a potato, the classic potato shape. You'll have to do some analysis. You have to actually get the moment of inertia matrix, which means knowing the mass distribution of an asteroid. And that's not the easiest thing in the world. So you might find that, okay, there's some direction here, and then there's a couple of directions. They all have to be orthogonal to each other, because I've said this is a 3x3 matrix, but it's also a symmetric matrix. And the eigenvectors of a symmetric matrix are all orthogonal to each other. So we'll talk about that at some later time. You could even do this for, if I were to take any shape and bend it. So if I take a flat plate and start bending it in weird ways, you could still calculate what this is. All right, so next, I think next time we're going to go to rigid body kinematics. This was just a brief intro to rigid bodies, sort of going through rigid body of particles, and then we'll go to some continuous limit. But we're going to carefully go through rigid body kinematics next. And now that we're all experts in how to use the transport theorem, it'll be easy. Actually, no, it's not. It's not. I admit it's difficult. So read the first few parts of chapter 3.